Okay, next video we are going to talk about what we call resonance structures. And that is when we have multiple Lewis structures for the same molecule. Multiple Lewis structures for the same molecule. All right. So you might remember back to SO2. We did the Lewis structure for SO2, and we got something that looked like this. We had a double bonded oxygen with 2 lone pairs, a single bonded oxygen with 3 lone pairs, and 2 lone pairs on the sulfur. Now, at the time, you may have wondered, well, why do we put the double bond to one side and not the other? And maybe even in class you would have asked me that. The reason is there is no good reason, okay? It actually has to go to both double bonds, or I'm sorry, both oxygens. So what we have is another equivalent Lewis structure, and I'm just drawing it in a different color to highlight it. It does not have to be in a different color, obviously. But basically, we've just drawn the Lewis structure with the double bond on the other side to the other oxygen, and we have separated it by that double-sided arrow. So every time you have a Lewis structure, you have to use that double-sided arrow to indicate that it is indeed a Lewis structure. So now what does this really mean? Does it mean that sometimes the double bond flips back and forth? Sometimes it's on one side, sometimes it's on the other side? No, absolutely not. There is no resonating here. What it actually means is that it's neither one of these, okay? It's the average of the two. So if we average them, what do we get? Well, it's very difficult to draw, which is why we don't typically draw it. But we get like this 1.5 bond, okay? Like I said, that's why we don't draw it. And I can't really draw the lone pairs there because on the oxygens. Okay, so these are like 1.5 bonds. They're not a double bond and they're not a single bond. And in fact, if we look at bond length and bond strength in SO2, that is what we find is that the bond length is somewhere between a single and a double bond, and the bond strength is somewhere between a double bond and a single bond. So we have evidence that that is indeed what is going on. So now I want you guys to do the same thing for NO3. So let me get you started. Or actually, if you would prefer, just pause the video now and do the Lewis structure for NO3 and do all of the resonance structures. There will be 3 structures in total. Okay, so coming back, I assume you did the Lewis structure and you got something that looked like this, where everything has a full octet and we have 1 double bond to 1 oxygen and then 2 singly bonded oxygens. And don't forget the brackets and the charge on the outside, okay? And then we separate them with the double-sided arrows, and we're going to draw 2 more Lewis structures. It doesn't matter which one I pick first. But we're just going to move that double bond around. There's more to it than that, of course. If you take OChem, basically if you're not one of the engineering majors in the class, or somebody else that doesn't have to take OChem, I guess, you will find out a lot more about resonance structures, and they're very important. So we just make sure that double bond gets to all the oxygens. And there we go. We have 3 equivalent Lewis structures, and there are such a thing as non-equivalent Lewis structures. You'll talk about that in OChem. But if we were to look at these, really we don't have a single bond anywhere on nitrate. We don't have a double bond anywhere on nitrate. We have like a 1 1/3 bond. So it's an average of all three, okay? And that's it for resonance structures.